Hello, everybody. Let me start by thanking the committee for the opportunity to present here some of my recent results on stochastic replicator dynamics. So what I want to discuss today is that apart from the biological motivation, there's also an intrinsically geometric picture in which stochastic replicator equations appear as natural dynamic. So in order to understand this geometric reasoning, I first want to give you some brief insights into what is called the Aitchison geometry. So the Aitchison geometry predominantly occurs in the field of compositional data analysis, which essentially is nothing but statistics of simplex valued data. And one of the big pioneers in that field was the Scottish statistician John Aitchison, and one of his main contributions, which in his honor is nowadays called the Aitchison geometry, is the following observation. So on the simplex, consider the following operations. We define P plus Q, which in the CoDa community is called perturbation of P by Q, in the following way. So P plus Q is defined as we take the component-wise product of P and Q, and after that we renormalize the vector in order to obtain again an element in the simplex. Likewise, we can define this sort of a scalar multiplication, and then it's easy to see that this triple del plus dot becomes an R vector space. The punchline is now that on this vector space, we can even further introduce an inner product, the Aitchison inner product, which looks like the following. And then what you end up with is an n-1 dimensional Hilbert space. So one way to see why that is actually true is to find an appropriate Hilbert space isomorphism. And the most classical or famous guy doing so is the CLR transform, which provides an isomorphism between the Aitchison simplex on one hand and the space H, which are just elements in Rn whose components sum up to 0, equipped with the inner product inherited from Rn. So now what's the CLR transform looking like? It's defined over here. So its ith component is just the log of pi over g of p, where g of p is the geometric mean of the simplex element p. So now there is, most of you likely have not seen this CLR transform before. I'm pretty sure that all of you will recognize its inverse, so which is written down here. So the inverse is an object which is popping up in quite a lot of different areas. So in physics, you would probably call this Boltzmann distribution. And for instance, in the learning literature, you can also find this guy as the softmax activation function. Okay, so now we've got an understanding of the Aitchison geometry, and what I essentially aim for in this talk is to study Brownian motion and other diffusion processes on the Aitchison simplex. Before addressing this issue, however, I'd like to insert a little intermezzo on a topic which is not too immediately related, namely deterministic replicator dynamics. So since we are here in the applications in biology section, I guess that most of you have seen that at some point. So we are given some fitness landscape and then deterministic replicator dynamics, or the deterministic replicator equation in a continuous time setting is this ODE system over here. And it was introduced in 78 by Taylor and Yonker, and is nowadays one of the most classical ways to reformulate Darwin's paradigm of selection in mathematical language. So particular well studied is the situation in which we have linear fitness landscapes. That is, if F is just given by some matrix or payoff matrix A. And you all also know that in particular in that situation, there are interesting and nice links between the dynamics given by the ODE or by the dynamical system on one hand, and by concepts of evolutionary game theory on the other hand, keywords, Nash equilibria, and evolutionary stable strategies. Okay, so now let's combine what we've seen so far. Here's the theorem. Consider X to be the solution of this Platonovich SDE over here. Then xt is Brownian motion on the Aitchison simplex. So now standing alone, this theorem is probably not too interesting, but the crux, of course, here comes if we combine it with a slide that we've just seen before. So because then what this theorem here actually tells us is that if we consider replicator dynamics within a white noise fitness landscape, then this dynamic is going to perform Brownian motion on the Aitchison simplex. So and in the figure above here, we've got one trajectory example of such a dynamic here, starting at the center. Okay, regarding the proof, I mean, it's almost trivial essentially. If we define xt to be the softmax of Brownian motion, then clearly this is going to be Brownian motion on the Aitchison simplex, simply because softmax basically is an Hilbert space isomorphism. And on the other hand, if you apply the Stratonovich chain rule to softmax of Brownian motion, and at that you use the property of the softmax function that it's Jacobian, can be nicely rewritten in terms of this G-1 matrix, which is the inverse Fisher matrix or inverse Fisher tensor, then you will easily be able to check that xt defined in this way is indeed going to solve the Stratonovich SDE that we've seen on the previous slide. Okay, so now we've gotten intuition of Brownian motion on the Aitchison simplex, and now we would like to study more general diffusion processes, for instance, by introducing some drift. So let's consider, for now it's just formal, this SDE on the Aitchison simplex. So we've got a deterministic drift part, which we then perturb randomly by additive Brownian increments. So here, this xt is again meant to be Brownian motion on the Aitchison simplex. So how should we understand such an equation? Well, we understand it, of course, in the same way as we would, for instance, understand SDEs in an infinite dimensional Hilbert space just by testing. So that is, we would say, y is a solution to this equation provided y is a solution to this integral equation over here for all p in the simplex. And now, of course, we may ask, well, can we also give a conventional description of such an Aitchison SDE, meaning in conventional Euclidean coordinates? And of course, that's possible, and basically just again an application of Ito's formula, which will tell you that y is a solution to the equation 1, if and only if y is a solution to the equation here in 2, which is not just a conventional Stratonovich SDE in Euclidean coordinates, if you like. So let me mention or stress one interesting thing here. If we look at equation 2, and in particular, if we look at the noise term, then here we have multiplicative noise in the sense that there is some diffusion matrix which depends on the solution, which acts on the Brownian increments. So that's different than equation 1. Here we have really just additive noise, right? So it's interesting to see that basically by this transformation, the nonlinearity, which is here hidden in this diffusion matrix, somehow enters this algebraic structure here. Okay, so now I want to give you one particular example of such a dynamic. Namely, let's consider F to be softmax of AP, where again A is some n by n payoff matrix. So if we plug this F in here in equation 1 and we use theorem 2, then to this diffusion on the Aitchison simplex corresponds in conventional coordinates the SDE that I've written down here, so that's equation 3. And that's an equation which people have studied before. It was introduced in 92 in a paper of Fudenberg and Harris, and since then it's called the stochastic replicator equation. And plenty of people have studied that equation afterwards, in particular Hofbauer and Imhoff. And the last slide that I want to present to you will be, in fact, a slide on this equation. So if we accept for now that this whole Aitchison geometry is somehow natural for that kind of diffusion, then we may probably wonder whether we can say anything about a contraction behavior of trajectories, for instance, right? In the sense that we measure distances with this Aitchison geometry. So therefore, let's consider the following two Wasserstein distances here. WA is the Wasserstein distance where we take as cost function indeed the squared Aitchison distance. And then we will also consider a second Wasserstein distance, namely the one where as cost function we take the conventional Euclidean distance squared. And so then here comes the last theorem. Let us consider mu t and mu prime t as laws corresponding to two solutions to this stochastic replicator equation that we've seen in equation 3 on the previous slide, both driven by the same payoff matrix A. Then, for instance, of course, we may ask, is it possible, or at least for which kind of matrices is it possible to bound this distance at any positive time by the distance of the initial data? Right? I mean, that's kind of a classical question. But as it turns out, this is a quite strict requirement on the matrices A, and in fact, in particular, in higher dimensions, there are not too many matrices for which this will be true. So indeed, here comes necessary and sufficient criterion. This bound holds if and only if A is of this form. So we've got this diagonal part, and then these two rank 1 matrices given by some vectors U and V. And now typically you would actually probably want to see something like an exponential decay factor here in front of this second, this right-hand side over here. And that you cannot get as long as you have WA on both sides. However, indeed, if this lambda here is strictly positive, then what one can prove is that if we take the other distance over here, then this guy indeed is going to converge to 0 exponentially fast. So the proof of that is a little bit more involved, and I was not able to put it into the 10 or 12 or 13 minutes. But if you want to see the proof and other interesting things regarding connections between this geometric perspective on one hand and applications to stochastic and deterministic replicator equations, then I invite you to have a look at the paper that I've written at the top of this final slide. Either it is already on the archive or it's going to appear there very soon. That's all from me. Thanks a lot and stay healthy.